In this video, I'd like to talk about the math question of the day for Sunday, July 16th, 2023. And with this problem, we need to solve this definite integral involving tangents and secants. And integrals like this are typically seen in a Calculus 2 class. So at this point, go ahead and pause the video, see if you can work through this on your own. And when you're ready, unpause the video and we can go through this together. Now, assuming that you've attempted the problem, let's start working through this. And the general idea is that we want to use different trig identities and a u substitution. Now, the strategy will depend on whether the tangent and secant are raised to even or odd powers. But we either want to make a u substitution where u is the tangent of z, so then du would be the secant squared of z dz. Actually, we can call this u1. Or we could make the substitution, which we can say is u2, that u2 is the secant of z, and then du sub 2 would be secant of z tangent of z dz. So this will be our general strategy, and we want to use one of these, again, depending on whether we're raising this to even or odd powers, either the tangent or the secant. Now, because we have an odd number of secants and an odd number of tangents, it will be simplest to pull out one tangent and one secant so that we essentially have the derivative of the secant function. And then we can use an identity to change all of the tangents to secants. And then substitute u for the secant of z. And the way that we'll relate all of the tangents to secants, we'll also need the identity that the tangent squared of z plus 1 is equal to the secant squared of z. Just the Pythagorean identity relating the tangent and secant functions. So let's start by rewriting this integral. We will have the integral from 0 to pi over 4 for our bounds with the variable z. And we're going to remove one tangent and one secant from these terms here. So we'll have the tangent of z to the 6th power multiplied by the secant of z to the 2nd power, and then we'll have our secant of z multiplied by the tangent of z. And again, the entire purpose of this is that now we have the derivative of the secant. So if we can put the rest of these terms all related to the secant, then we can just set u equal to the secant of z and put everything in terms of u. So let's now focus on this tangent of z to the 6th power. We can rewrite it using this identity here. If we solve this for the tangent squared of z, this will be the secant squared of z minus 1. And we can rewrite this as the tangent squared of z to the 3rd power. So let me make just a bit more room. We'll keep our identity on the screen here. But this integral still goes from 0 to pi over 4, but now we'll have the tangent squared of z, and we'll raise all of this to the 3rd power, and I'll just rewrite the rest of this. So from here, let's just replace this tangent squared of z with the secant squared of z minus 1. So we still have that integral from 0 to pi over 4, but now we have the secant squared of z minus 1 all raised to the 3rd power. And again, I'll just rewrite all of these secant terms multiplied together and then multiplied by the tangent of z dz. And at this stage, now because we have the derivative of the secant function and everything else is in terms of the secant function, we can just set u equal to the secant of z. So let's say u is the secant of z, then the differential du would be the secant of z multiplied by the tangent of z dz. So we can replace this part here, the secant of z times by the tangent of z dz, with just du, and then each of these secant functions will be replaced with u. So let's now rewrite this integral again. And we'll need to change the bounds, but let's come back to that in a moment. We have u squared minus 1, and all of that is to the third power. Then we multiply by u squared, and we have du here. So we've transformed this integral into essentially just a polynomial now, and we can multiply all this out so that we can then use the power rule. So let's start by first just rewriting this u squared minus 1 to the third, and we can actually multiply it out. So let's rewrite it 3 different times, and we could use the binomial theorem here if you want. But we'll multiply these first 2 terms. We get u to the fourth minus 2u squared plus 1. And then all of this will be multiplied by u squared minus 1. So let's distribute the u squared first. We get u to the sixth minus 2u to the fourth plus u squared. Then let's distribute the minus 1. We get minus u to the fourth plus 2u squared. Let me make a bit more room here. And then we get minus 1 at the end, so we can combine like terms. Let me again make just a bit more room. So this will be equal to u to the sixth, and then we've got 2 terms with u to the fourth, so we have minus 3u to the fourth. Then we've got 2 terms with u squared, so plus 3u squared, and then we have minus 1 at the end. Though, like I mentioned, if you want, you could just use the binomial theorem. And we're going to multiply all of this by u squared. So let me rewrite this integral now. We can go down here, and we'll rewrite it after distributing u squared each of these. So we get u to the eighth minus 3u to the sixth plus 3u to the fourth minus u squared, and we have du. And if we want, we could put our bounds in terms of u here, since we know u is just the secant of z, and we know that z starts at 0 and then z goes to pi over 4. So if we plug in 0, when z is 0, u would just be the secant of 0, which is 1, since secant is just 1 over cosine, and the cosine of 0 is 1, so you get 1 over 1. And when z is pi over 4, the secant is the square root of 2. Since, again, it's 1 over the cosine, and the cosine of pi over 4 is root 2 over 2. So you flip that over, you get 2 over root 2, which is the square root of 2. So our bounds go from 1 to root 2. But if you want to ignore the bounds and evaluate this integral and then substitute back in u for the secant of z, you can then use the original bounds. But in either case, you'll get the same answer. So let's evaluate the integral now. We use the power rule. We raise the exponent by 1 and then divide by that new number. Here we raise it to the 7th power, then divide by 7. This goes to the 5th power. We divide by 5, and this goes to the 3rd power. Divides by 3, and we go between 1 and the square root of 2. So let's keep making a little bit more room. This now is a bit of algebra. We're just plugging in our numbers here. We're using the fundamental theorem of calculus. We'll evaluate it at the top bound and then subtract everything evaluated at that lower bound. So let's first plug in the square root of 2. We would get root 2 to the 9th power. Let me rewrite that. All divided by 9 minus 3. We get root 2 to the 7th power over 7 plus 3/5 of root 2 to the 5th power minus 1/3 of root 2 to the 3rd power. So that's our upper bound, and then we subtract everything evaluated at that lower bound. And since we're plugging in 1, it's not too bad. We get 1/9 minus 3/7 plus 3/5 minus 1/3. So we just have a lot of fraction arithmetic here. And with the square root of 2 to various powers, every time we pair it up, for instance, root 2 squared, that's just 2. Or we could also think that we have 2 to the 1/2 power, and when we have an exponent to an exponent, we multiply. So we have 2 to the 9/2, which we can rewrite as 2 to the 4th multiplied by the square root of 2. We have 2 to the 4th times by 2 to the 1/2, which is 2 to the 4.5 power, or 2 to the 9/2 power. So essentially, every time we can pair them up, we can pull out a 2. And that's divided by 9. We have 3 multiplied by 2 cubed multiplied by root 2. And that's divided by 7 plus 3/5 multiplied by 2 squared multiplied by root 2. And we have minus 1/3 multiplied by 2 root 2. And again, this is just fraction arithmetic. If we add and subtract these fractions and then simplify, we get minus 16 over 315. You can use your calculator to do this and then convert your answer back to a fraction if you have that function on your calculator. Now, looking at this expression here, what we can do, since each of these have a square root of 2 in it, we can just factor that out. And 2 to the 4th, that's 16. And 2 cubed, that's 8. We get 8 times 3, which is 24. So we have 24 over 7. We have 4 times by 3, that's 12. Divide that by 5. And we have 2/3 here. And all of this we will subtract by 16 over 315. So again, we can use a calculator for this, or you can do it by hand if you want. But once you use your calculator or do it by hand, you'll get the square root of 2 multiplied by 26 over 315. And we'll subtract 16 over 315. So if we want, we can actually put this with one denominator. We would get, as a final answer, 26 root 2 minus 16, and then all of this is over 315. And actually, from here, I realized I made a very slight mistake. We are subtracting this negative number. So actually, we are adding here in all of these. And so this right here would actually be our final answer. And if we want an approximation of this, we can plug this into our calculator and get approximately 0.1675. And it will be irrational because of the square root of 2. So technically the decimal goes on forever. It is infinite, but this works pretty well as an approximation.